It is the second part of section 9.1. Here we'll consider properties and some computational techniques for the singular value decomposition. Let's see the theorem. A is on n by n metric, and U sigma V transpose is the singular value decomposition of A with all positive singular values. Then we say rank of A is R, and null space of A is from right singular vectors. We collect here V R plus 1 to Vn. That is null space, the basis of the null space. And range is, now A, already we know that earlier, A, Vj is sigma j, now Uj, of course j is from 1 to now R. Okay, so that is vector in the range, so that all the points in the range is spanned by U1 to UR. A can be written in this way. That is called dyadic decomposition. We considered earlier. Now, if we try to measure a 2 norm, then that is the same as the first singular value. That will be a good exercise for you. And I gave you a hint so that you can prove that. And exercise 9.7 is asking you to prove this one for Venus norm. Also, it will be a good mathematics. Now, if you are trying to get minimum of this quotient, then that is same as sigma n. Once R is strictly less than n, then that must be 0. Okay, again here, A is on n by n metric with rank R, and A is U sigma V transpose, the singular value decomposition, with here sigma 1 to sigma R positive. And we can define AK, that is from 1 to K, that the sum of rank 1 matrices. Once you are using R, then that is the original metric. It can be written here, summation up to R. Now we try to choose only K component. So K is smaller than R. K is from 1 to R minus 1. Okay, AK is an approximation. So A1 is only one component, one rank 1 metric. A2 is the sum of 2 matrices, and so on. Then here AK has a rank K, and then the difference, okay, from A to AK, the difference measured in L2 norm is now minimum among every difference between A and B having rank bounded by K. That means that AK is best approximation of A once we consider rank K metric among every possible rank K matrices. AK is the best approximation, and then the difference is now exactly sigma K plus 1. And once AK is considered, then ignore the part. The first one start with sigma k plus 1. So that is related with, for example, that one. So A norm is a sigma 1 because it starts from sigma 1. Now, once from AK is subtracted, then, okay, now A itself, okay, we can write this one in this way. A itself is, summation is from 1 to n. Now, 1 to k is subtracted, which means that the remainder part is from now k plus 1. Oops, I'll rewrite it. Okay, now that is j is from k plus 1 to r, and sigma j and uj vj transpose. So the first one is sigma k plus 1. So that is the quantity. Okay, and this is also true even we measure the difference by using Frobenius norm. When you are measuring Frobenius norm, you have to consider every singular value square sum once it's squared in. So that is now here related with this one. Okay, that is of all matrices of rank k, and AK is closest to A, the best approximation. Okay. The metric AK can be written in this way, so that now, okay, here we try to use U and V transpose, and then sigma K is we are collecting only the singular values from sigma 1 to sigma K, and we ignore and put it 0, then this multiplication will be same as that one. Is K, upper bound is K. So it can be written in this way. Okay. Now, how to compute the singular value to conversion? This one is a kind of a classroom example, but in reality, this method is not being used. Once the metric dimension is large, like 1,000 or even 1 million, then this technique is yet expensive. Later on, we'll see how to get better way. But for small classroom examples, first we form a transpose A. If M is larger than or equal to n, then this one is n by n square metric, and this metric is called covariance metric of A. To be a covariance metric, in fact, it must be from the center, so that now for each column, you have to subtract the mean, and then you have to organize a transpose A. Then that's the original definition. However, conventionally, we say, again, a transpose A itself is a covariance metric. Okay. Now, for this covariance metric, we'll try to find eigen decomposition. That means that here there's a diagonal metric of eigenvalues, and then V transpose. V is the collection of eigenvectors. That is orthogonal metric. That means here having this property. Okay. Now, the entry of this lambda is lambda 1 to lambda n. And we already know that the singular value is the square root of the eigenvalues of A transpose A. So to get the singular values, just take a square root, and we get sigma j from lambda j. So we found so far the right singular vector and sigma, and left singular vectors can be found by using this identity. AVJ is the same as sigma j uj from algebraic interpretation, so that by using that we can get here uj is 1 over sigma j a vj. Okay. uj is an eigenvector of A transpose, and earlier we figured it out, but the alternative computation of uj in this equation is more efficient. Rather than trying to find the eigenvalue, eigenvector of that metric, this metric is m by m metric. Usually m is larger than n, so that is a larger metric. So it's more expensive. Okay. Now, in this computation, we can get only now up to rank. Once rank is k, then we can get only k vectors. And of course, over there, we can get only, now, we have that, but now, once rank is k, then from sigma k plus 1, the value will be 0. So we can get only k vectors. But if we want to make n vectors for u, then you can expand. No matter how you expand the left singular vector, it doesn't matter. Eventually, when you are trying to use this singular value decomposition, the corresponding singular value is 0, so that there's no effect later on. So here, if necessary, pick up the remaining columns of u, so it becomes orthogonal. These additional columns must be in null space of A transpose. You can expand it, but anyway, here, no matter what it is, usually it doesn't matter. Okay, here, in this example, we'll find the singular value decomposition for A 3 by 2 metric. First, we form A transpose A, and now the characteristic equation of A transpose A, and if we solve this equation, then we have 18 and 5, 2 eigenvalues of A transpose A. And now for each one, the corresponding eigenvectors are given in this way. So once it is normalized, and also this one, then now we can collect them in this metric, which is right singular vector. Now for eigenvalues, we take a square root to get singular values. So we have sigma. Now u1 is 1 over sigma 1, a v1. So we practically compute it to get that. And then u2 is 1 over sigma 2, a v2, and we recheck this one. The collection of these two vectors will be left singular vectors, left the singular metric u, so that we have u sigma v transpose. So once you multiply them, then you can get original one. Okay. Now here is how to get singular value decomposition in practice. That one is well organized. This technique is derived and completed by a very genius person, Gene Garlock. He spent really long time in numerical linear algebra and made a wonderful contribution to the society. Because of his contribution, we can enjoy modern, very powerful computation. I guess he's the really most contributing guy in the society. Okay, so we have to appreciate his contribution. Okay, here in real world, the computation has two phases. First, we try to transform the given metric into, that's called upper bidiagonal. Upper and bidiagonal, two diagonal here lines, so the upper part, so it is called upper bidiagonal metric. And by using some technique, we transform this one over there. And then from here, we try to find now singular value and or some eigenvalue and eigenvectors, and try to find required and the vectors, and then now transform back. Then that will be here the singular value decomposition. That's how the computation is being done nowadays. Okay. So phase one is constructing to find the sequences of household transformations to find an upper bidiagonal metric, so that front backside multiplication, and then we recheck over there. And these are transformation, so that after finding now the required information from this B metric, and then transform back to get the SVD for original metric. Okay, that's how the computation is working. This technique is extremely stable and also not so measurable in computational complexity. If we want to get everything, then that is this cost. There's m squared n and m term. There's no m. But anyway, in any case, it's a third order altogether, m squared n, mn squared, and cubed. It's not so measurable. If we want to get only v and sigma, then now here, that one is almost, this one is ignored. Okay. Now phase 1 and 2 take order mn squared and order n squared flops respectively, and then here phase is done, 2 is done when, okay, in fact over there, when phase 2 is done with order n iterations. Okay. Okay. You can use the built-in the programs in Python and NumPy, linear algebra, SVD. You'll get in this way USV. Now in MATLAB or Maple, you can use SVD. And now for mathematical, okay, this is a long command. By using this one, you can get singular value decomposition. Okay, here we have numerical rank. in reality, 0, singular value, is not easy. Singular value, although theoretically is 0, but in reality, during the computation, round of error may be involved, so that is not 0. So that we have to decide, and if the value is 0, once it's small, then we have to have really good guideline to decide whether it is 0 or not. For example, in this matrix, first column, second column, and then if you add these two, then you will get the third one. So every over there, every in horizontal direction, if we add, then you can reach it over there, add, then reach over there, and so on. That means this matrix is rank 2 matrix because only it has 2 independent columns, and last one is a summation, so that depending. So it has a rank 2. Now, if you are using SVD in MATLAB, then the output here, sigma 1, sigma 2, okay, these two are reasonably large. However, the last one is 8 times 10 to the minus 17. So you have to decide the rank 2 or rank 3. But what if this sigma 3 is, for example, 10 to the minus 13 or 10 to the minus 15? Then can we say that yet it is rank 2? That's really a question. Now, to eliminate such doubt and questions, we have some convention. And now we'll see the MATLAB convention, but Python also is adopting the same. So once you understand, then now you can understand the other convention in other languages. Okay. Now, by using threshold, we have to decide. Now, if you call the rank command, then inside such a threshold will be made. There's twice, and maximum of m and n. Then epsilon is the unit round of error, and a 2 norm. We already know a 2 norm is, what is this one? Sigma 1. Okay. Now, epsilon, the unit round of error, is 2 to the minus 52 for double precision. So it is about 10 to the minus 6, twice of 10 to the minus 6. So that for the example here, the metric, already we know sigma 1 is 2.5987. Okay, use that number. Your threshold is twice mn, 5 times 3, mn are 5, 3, so that maximum is 5, and epsilon is this number, and then here a2 norm is 2.5987. Once we multiply them, we can get here 5.7 times 10 to the minus 15. So once the singular value is larger than this threshold, then we consider it positive. But it's smaller than it, then we consider it 0. So that for this example, now this is smaller than the threshold, so we have rank 2. Okay. This is end of the section. Thank you.